Alright, what up guys? Welcome back. I'm going to be breaking down another passage. This passage is from Blueprint. Okay, this is from their diagnostic test. When you make a Blueprint account, you get a diagnostic test and you get a whole entire full-length exam. Okay, for free when you make an account. So I'm going to be breaking this down. Alright, I'm going to show you guys how to read through the passage, how to make it make sense, where to highlight. Okay, I'm going to show you guys how to pick the best answer choice, especially when you're stuck between two different answer choices. I'm going to show you guys how to do that. How to make it make sense, how to dumb it down in simpler terms. All right, because I know you guys have a lot of problems with passage breakdown. I'm going to show you guys the timing as well. All right, so before I begin, I want you guys to go ahead, read through this passage first, go through the answers, go through the questions, all right? Write down your answer choices, see where you messed up. Write down, be like, hey, I didn't understand this. Or be like, hey, I was stuck between these two answer choices and I chose this one and I got it wrong because X, Y, and Z. Okay, so I'm going to go through this here. All right, read through this passage. All right, I'm going to go through the questions now. Write down your answer choices. All right, this is question 14, 15, 16, 17, 18, and all right, yeah, that's it, 18 only. Okay, so go through it, pause the video whenever you need to. All right, I'm going to break this down right now. Okay, now note, all right, the pace that I go through and read this should be more or less the pace that you go through these passages, okay? I want you guys to not necessarily be a slowpoke when you read these passages, okay? But go a little slower, like you're reading a book, just like you're reading your normal book, okay? But a little bit slower so you can really understand what's going on. So you can read this once, okay? And not have to go back and reread and not understand, okay? You want to read it once, full time once, and try to get a decent understanding of what's going on, okay? And these questions here, these are straightforward. These should take not that much time, okay? These should be like read, this one, okay? Here, take a little more time. Questions, fairly straightforward. You should knock them out. All right, enough talking. Let's do this. Beta-Lactam antibiotics like penicillin are derived from fungi, which use the molecules to defend against environmentally borne diseases. Once discovered, these antimicrobial agents were quickly employed by physicians to treat pathogens which invade humans. Okay, cool. I already know all this. These molecules are typically formed via intramolecular attack within an amino acid and secondary reactions between amino acids. All right, I'm going to highlight this. Why am I highlighting this? Okay, I'm highlighting this because it stuck out to me. Whenever something strikes out to you, you highlight it. And the things that usually strike out to you are those that involve your content review before, like, hey, intramolecular attack. Okay, secondary reaction between amino acids. All right, I've seen this before in my content review, so I'm going to highlight that because maybe one of these questions are going to involve asking like, hey, do we have inversion or retention of stereochemistry? And then you're going to have to look and see, hey, where's the reaction? Boom, it's right there. Okay, so just in case, I'm going to highlight that. Let's keep going. The lactam designation refers to the cyclic amide ring found in the molecule. All right, you should know this from your content review, but they threw it in here. Okay, that's cool of them. Penicillin-like drugs are analogs of amino acid residues located on bacterial cell walls. The structural similarity between beta-lactam antibiotics and these residues facilitates their binding to the active site. Okay, active site. Let's highlight that. In the machinery required to build the peptidoglycan wall. All right, and they give you the structure of penicillin. Here's the amide. Cool. These beta-lactam molecules are particularly reactive due in part to significant ring strain. Okay, I've seen this in my content. This is striking out to me. I'm going to highlight it. Nearby nucleophiles can be acylated by the ring, allowing the ring to open. Cool. Important stuff here, guys. They're giving you a reaction. The antimicrobial efficacy of penicillin lies in its ability to acetylate serine residues on enzymes that bacteria require for normal cell wall production. Acetylation, baby. We acetylate those serine residues. Okay. During the acetylation of serine, the amide on penicillin is converted to an ester. This causes binding and locking of the molecules. Okay. What's going on here? Important. All right. the acylation of serine. Serine gets an acyl group attached to it. Okay, and what does that do? What does that do? The amide on penicillin is converted to an ester. This causes binding and locking of the molecules, which prevents serine from activating the cell wall synthesizing enzymes. An intact cell wall is necessary for bacteria to stay alive. Okay, now I already know what's going on here. All right, I read this and I know what's going on here. Okay, serine, all right, has an OH group. You should know that. All right, here they give you the structure of serine. So serine's, this OH group is going to go attack. Okay, it's going to go attack. It's going to open the ring, and that's going to be locked. It's going to be locked down. Okay, because it's locked down, that's going to stop the bacteria from creating its cell wall. And if the bacteria is stopped from creating its cell wall, the bacteria is going to die. That is how the antibiotic works. No need to complicate it. Okay, no need to complicate it. That's exactly what happens. Okay, simple. Dumb it down in your terms. All right. So, I mean, I should have highlighted this. Okay, I should have highlighted binding and locking. All right, I should have highlighted this one right here as well. Okay, so in your own words, dumb it down. Dumb it down in your own words. What's going on here? Okay, bacteria needs to create cell wall to live. Okay, it's shown right here. An intact cell wall is necessary for bacteria to stay alive. Bacteria need cell wall to live. What does penicillin do? Penicillin, okay, gets in the way, causes a serine to attack the penicillin. Serine is on the bacteria. When serine goes and attacks the penicillin, all right, it's going to open the ring, and because it opens the ring, it's going to stop the bacteria from making its cell wall. No cell wall, no life. That's what penicillin does. Cool, simple, that's it. Let's keep going. All right. So honestly, this passage wasn't that bad. This is a pretty good passage. All right. It has a lot of organic chem here. I know you guys are weak at organic chem. All right. Question 14. At which nucleophilic site is serine most likely to be acylated by penicillin? All right. This one, you have to know how nucleophilic, electrophilic reactions work. Okay. Here's your serine here. Okay. Serine, tyrosine, what was that? Okay, the amino acids that have the hydroxyl group, that's important because these can go and act as a nucleophile and attack things. Okay, what do they usually attack? All right, there's not many organic chemistry reactions you have to know for the MCAT. All right, these are going to go ahead and attack, let's say, a carbonyl. Okay, these are going to go ahead and attack a phosphate group, let's say. Let's say there's a phosphate group here. All right, it's going to attack the P in the phosphate group, okay? That's why those amino acids are important. That OH is very nucleophilic, okay? So easy, straightforward question here, guys. It's going to be the side chain OH. That's going to be the nucleophile. All right, carbonyl carbon, no. Carbonyl OH, no. Alpha carbon, no. Okay, you should know your organic chems is pretty simple, pretty obvious. It's a very important reaction, very high yield, okay, that you should know that. Let's keep going. Early research into the mechanism of antibiotics theorized that it was implausible that the amide in penicillin would convert to an ester. Which of the following explains this doubt? All right. You see how they worded this? Okay, if you read this one time and you understood what they were saying, cool for you. Like, you have good reading skills. All right, but if you're somebody that's like, had to read this and you're like, what? Let me read it again. Okay, dumb it down. Dumb it down. All right. They're saying that, hey, okay, the amide in penicillin, it's implausible that's going to convert to an ester. There's no way that amide is going to convert to an ester. There's no way. No way. That's what these researchers are saying. All right. No way it's going to convert. All right. Why? All right. Why? So let's go ahead, go through the answer choices here. Let's start off with the first one. Amides possess better leaving groups than esters. Esters possess poor leaving groups than amides. Okay, you should know, this is straight up content, you should know the ranks of the carboxylic acid derivatives. Okay, what's the most reactive, what's the least reactive? All right, we're going to start off with the most. No, this is the least here. All right, the first one is going to be your acyl halides. And then it's going to be your anhydrides, I believe. Yeah. Anhydrides. And then it's going to be your esters. That's number 3. and then it's going to be your amides. Okay, this is the most reactive, this is the least reactive. All right, just like everything in all your MCAT content review, okay, we always want to go to where it's most stable. All right, that's usually how reactions work. They want to go to where it's most stable. What's most stable? It has low energy. Okay, that's how usually almost every organic chem, also in physics, electrostatics, all that works. Okay, we always want to go to where it's more stable. All right, so if this is the most reactive, remember, is the most reactive, is the least reactive. Okay, the reactions for the carboxylic acid derivatives are always going to go to where it's least reactive. It's going to go from here to here, here to here. Okay, maybe here to here. Okay, I don't want to overcomplicate this for you guys, but that's usually how it goes. All right, so let's see. Amides possess better leaving groups than esters. Okay, amides possess better leaving groups than esters. That is not true. That is not true at all. Okay. This is how, oh god, I'm like teaching you guys organic chem right here. All right, but fine, whatever. Okay, but this is like 2 times speed. Okay, I'll go through this quick. All right, let's see. So all the carboxylic acid derivatives, okay, let's say you have an amide here versus, let's say you have like an ester here. Okay, let's say you have an ester. That's an ester, this is an amide. Let's throw an H here. And let's throw an R group here as well. All right, what makes a good leaving group? Something that wants to leave, okay? Something that wants to leave, wants to be a good leaving group. How do I know if it wants to leave? Well, you could follow the rule, all right? Usually, weak bases are good leaving groups, okay? The conjugate base of strong acids are good leaving groups, okay? Or you can also look at it, all right? Look at it, let's see. This guy has high energy. This guy also has high energy. Which one has more high energy? Which one does not want to be there at all? All right. Remember, the one that has high energy, one that is least stable, wants to leave to become more stable. Everything always wants to go to where it's most stable here. All right. So I don't want to get into too much detail, but all right. Let's go ahead. The ester is a better leaving group than the amide. Okay. Ester is more reactive than the amide. So an ester would want to leave more than an amide. Okay, got it? Cool. Don't overcomplicate it. All right, I don't want to take too much of your time, but let's keep going here. All right, so that's how it is. Actually, let's make a mnemonic for this as well. If you have a better mnemonic, let me know. I'm going to make one right now. And, all right. My hermit crab, Alfred, eats algae. Okay, my hermit crab, Alfred, eats algae. Okay, that's the most reactive to the least reactive. All right, halides, acyl halides, anhydrides, esters, and then amides. Okay, cool. That's a nice mnemonic. If you have a better one, let me know. Okay, all right, let's get to this question. Too much time wasted here. Amides possess better leaving groups than esters. We know that that's false. Esters have a better leaving group than amides. They're more reactive. A is wrong. Esters possess poorer leaving groups than amides. Okay, this is wrong as well. All right, good thing here. Good thing to notice, guys. All right. When you have 2 answer choices that basically say the same thing, they're both wrong no matter what. Okay, they're wrong. They're both wrong no matter what. These are basically saying the same thing here. Okay. If you ever have that, they're wrong. That's it. Don't even second guess it. They're wrong. Okay. You cannot have that in the question answer choices. See, amides are less reactive than esters. Well, if you know the order, you're going to know that amides are less reactive than esters. Okay. These are more stable. Therefore, they're less reactive. So C is the answer. And then serine contain no good nucleophiles. Okay, that's obviously wrong. This is a great nucleophile here. All right, so D is just wrong here. All right. Let's erase all this. All right, cool. Next question. Oh, all right. Which of the following must be true if the penicillin-serine reaction locks in the ester formation as described in the passage? All right, if it locks in there. All right, we want to form the penicillin-serine ester. We want to form that. We want to form this. All right, because if this forms, then it's locked. All right, so the thermodynamic cost of breaking the penicillin-serine ester is larger than the thermodynamic release of amide formation. All right, so dumb it down, guys. Dumb it down. This is saying it requires a lot of energy to break the penicillin-serine ester than it is to release and make the amide. Okay, so I'm gonna break this down. All right, for me, whenever I read these words, I get a little tripped up. Okay, so I'm just gonna break it down. All right, if the thermodynamic cost of breaking the penicillin-serine ester is large, then this means, okay, cost, we need energy. So this is gonna be a delta G. We need energy. It's gonna be positive. It's gonna be a big positive. All right, so it's very non-spontaneous to break the penicillin-serine ester. Okay, it's very unlikely that we're going to break the penicillin-serine ester, which is cool. That's what locking means. We want to keep that penicillin-serine ester. Okay, I don't want to break it. This is telling me that it needs a lot of energy to break it. Okay, which is cool. I like that. All right, this makes sense for me. It is larger than the thermodynamic release of amide formation. All right, it's larger, it's more likely to not break the penicillin-serine ester than it is to make the amide formation. So this is a good answer choice. I like A, but let's keep going. The thermodynamic release of forming an amide is equal to the thermodynamic cost of forming an ester. This is completely wrong. Okay, if it was equal, then you're gonna have opening and closing of the ring and all that stuff. Okay, that's not good. That's not good. B is wrong. Okay, I'll strike through that, John. The thermodynamic cost of breaking the penicillin-serine ester is smaller than the thermodynamic release of amide formation. Okay, dumb it down, guys. What's it saying? The thermodynamic cost of breaking the penicillin. All right, so this is saying the opposite of this one. It's saying that it's going to be non-spontaneous, small. Okay, so it's not going to be favorable to break the penicillin-serine ester, but it's going to be, let's see. Oh, okay. So this is basically saying that it's also a delta G is positive. It's non-spontaneous to break it, but it's small. Okay, this one said it's large. It's very non-spontaneous that we're going to break it. It's very unlikely we're going to break it. This one is saying it's unlikely we're going to break it, just a little bit. Okay, it's smaller than the thermodynamic release of amide formation. So this is saying we'd rather form the amide than go ahead and break the penicillin-serine ester. Okay, we'd rather form the amide. That's what it's saying. We don't want to form the amide. We want to form the penicillin-serine ester. So this one is wrong. All right, this one is wrong. D. The thermodynamic release of forming the penicillin cyclic amide is larger than the thermodynamic release of breaking the penicillin-serine ester. Okay, they're saying that it's very spontaneous to make the amide rather than, and it's also spontaneous to break the serine ester. Okay, that is wrong. Okay, they're saying that it's larger, it's more spontaneous to form the amide. Again, we don't want to make the amide. We want to make the penicillin-serine ester. Okay, so this is wrong. This one went over is wrong. A is answer choice. All right. Which functional group is not found on penicillin? Here's penicillin. Okay, cool. Straightforward question. Waste no time on these, guys. Boom, penicillin, amide, right here. Imine this is an imine. It's like an R, anything double bonded to an N, and this is also bonded to something else. Okay. Is there a double bond to an N? No, there's not. Okay, I'm gonna go with this one. Carboxylic acid, it's right here. Thioether, it's right here. Okay, answer is B. On the penicillin heteroatom ring, all right, what is the absolute configuration of the carbon labeled one? Right, here's one. All right, now there's two ways to do this. There's a complicated way and then there's an easy way, okay? I'm gonna break this down in steps for you guys. All right, step one, counterclockwise or clockwise. Step two is H front. That's all you gotta do, okay? So there's an H here. Okay, if this is a dash, this one has to be a wedge. All right, you can't have two wedges or two dashes. So let's go ahead. Nitrogen. So what are we doing? Carbon, nitrogen, carbon, hydrogen. Who wins? This guy is heavier than carbon. So one's gonna be here. What do we have now? We have a carbon, a hydrogen, and a carbon. Okay, we have a carbon and a carbon, so they tie. So we move on to the next element. This carbon is bonded to a sulfur. This carbon is bonded to an oxygen. Sulfur is bigger than oxygen, so this one is number 2. Okay, this carbon is number 2. And this one has to be 3. All right, and then the hydrogen has to be 4. All right, whatever is bigger to whatever's the smallest, that's it. So it's a little hard to see here, but this is 1, this is 2, and this is 3. So 1, 2, 3. All right, this is clockwise or counterclockwise. This is clockwise. Clockwise is R. Is hydrogen in front? The hydrogen is in front. So what does that mean? If it's in front, you have to flip the R to the S. Okay, if it's dashed, if it was like that, okay, then you wouldn't have to flip the R to the S. Okay, so since the hydrogen is in the front, we're going to flip the R to the S. Answer is C. Okay, what about A and B? A and B refer to how it rotates plane polarized light. Okay, just because something is positive, all right, just because it's positive doesn't mean it has to be S. Just because something is negative doesn't mean it has to be S. These have no relation to each other. These are found out experimentally. Okay, so that's S. That is it. All right, we're gonna go ahead and see if we got everything right. Okay, I do this, guys. I've never seen this passage before, but I want to see if I got everything right. So I'm gonna check that right now. All right, let's keep going here. Oh,